In this lecture, we'll be discussing about another classic problem of synchronization, which is known as the dining philosopher's problem. So first of all, we'll be trying to understand what is this dining philosopher's problem, and then we'll be seeing if we can solve this using semaphores. Alright, so first let's see what is this dining philosopher's problem. So in this dining philosopher's problem, what we have is, we have a round dining table in which we have, let's say, 5 philosophers who are seated around the table like this. So the philosophers here, they can be in two states, which is the thinking state and the eating state. So the philosophers here, they spend their whole life either thinking or eating. So when the philosophers are thinking, they don't interact with their colleagues here. They just mind their own business and they think. And when they are hungry, they will try to eat this rice or noodles that are present in the plate that is placed before them. Now the thing is, when the philosopher wants to eat the food that is placed in front of them, they need to make use of these forks or the chopsticks that are there that are placed adjacent to them. So when a philosopher wants to eat, he needs to make use of 2 forks or 2 chopsticks that are placed here. They cannot eat with just one, but they need 2 of them. So when a philosopher gets hungry, he will take up the 2 forks or chopsticks that are adjacent to him at his right and left, and then he can start eating. So when he starts eating, nobody can disturb him or nobody can take the fork away from him. And then when he finishes eating, he will be placing the forks or chopsticks back at their places. So what is the problem here? So if you look at this diagram carefully, we can see that the chopsticks or the forks are limited. There are 5 philosophers, and how many forks are there? 1, 2, 3, 4, 5. There are only 5 forks. And I told you that when a philosopher wants to eat, he needs to make use of 2 forks or 2 chopsticks. So clearly we see that it is limited. Like for example, when philosopher 1 will want to eat, he will make use of this and this fork. And at the same time, if philosopher 2 gets hungry, this philosopher 2 needs to make use of this fork and this fork. But we see that this fork is being used by philosopher 1. So he will not be able to eat when philosopher 1 is using the fork that is adjacent to him. So we have to make sure that no 2 philosophers that are adjacent to each other try to eat at the same time. So if they try to eat at the same time, we are going to have a problem. So as I told you, the philosophers can be in 2 states, the thinking state or the eating state. So when a philosopher is thinking, he does not interact with his colleagues. He just minds his own business and he thinks and he does not disturb anyone. And now when he eats, what happens? When a philosopher gets hungry, he tries to pick up the 2 forks that are closest to him, left and right. A philosopher may pick up only 1 fork at a time. So this is also an important thing. He needs 2 forks for eating, but also he cannot pick up both the forks at the same time. He will have to pick up 1 fork and then after that he'll have to pick up the other fork. So that is also an important thing that we need to keep in mind in this problem. And also, one cannot pick up a fork that is already in the hand of a neighbor. So that also I've already shown here. When a fork is being used by one of the philosopher, no other philosophers can use that particular fork. So I told you, like when philosopher 1 is eating, he'll be making use of this fork and this fork, which are at his right and left. So at the same time, if philosopher 2 tries to eat, he also needs to make use of this fork and this fork. But this one is held by philosopher 1. So 2 will not be able to eat because he will not be able to get hold of this when 1 is eating. So that is what we mean here. And then when a hungry philosopher has both his forks at the same time, he eats without releasing his forks. When he has finished eating, he puts down both of his forks and starts thinking again. So when a hungry philosopher gets hold of both the forks, he will be eating. And after he completes eating, he will be placing the forks back where they were. And then he will start thinking again. So this is the scenario that we have in a dining philosopher's problem. So what is the actual problem here? I have already told you. The problem is that since the forks are limited, no 2 adjacent philosophers should be allowed to eat at the same time. So no 2 philosophers should try to access the same fork at the same time. So that is the problem that we have here. Okay, so now you may be thinking, why are we discussing about this dining philosopher problem? Why are we creating a story like this and why are we trying to solve this problem? So if you think about it, this is actually a problem of operating system which deals with resource allocation. So here all these philosophers, they represent processes, and the forks or the chopsticks that are placed here, they represent resources that has to be shared between processes. So we see that we have limited resources and they have to be shared between processes in a synchronized manner without violating any rules. So there may be resources that can be used by only one process at a time. So if other processes try to access the same resource at the same time, then we will be having problems in the operating system. So that is why we are discussing about this dining philosopher's problem. It is actually a problem of resource allocation and how the resources are being utilized when they have to be shared among processes. Alright, so now we have understood the problem statement of this dining philosopher's problem, and now we will be seeing how can we solve this using semaphores. So one simple solution is to represent each fork or chopstick with a semaphore. So we know that a chopstick or a fork should be used by only one philosopher at a time, and when one philosopher is holding it, no other philosopher should be allowed to take it away from him, and it should not allowed to access that same fork at the same time. So we can do that with the help of semaphores. So a philosopher tries to grab a fork or chopstick by executing a wait operation on that semaphore. So now what we'll be doing, we'll be representing each of these forks or chopsticks with the help of a semaphore. So we already know the features of semaphore and how they work. So when a philosopher wants to grab a fork or chopstick, he will be executing a wait operation on the semaphore or the chopstick. So we know what happens when a wait operation is executed on a semaphore. So when a wait is executed, it implies that that particular process wants to use that semaphore and it wants to get hold of it. And when it gets hold of it, no other processes will be allowed to use that semaphore. So similarly, we'll be applying this on the chopsticks or the forks that we have here. So the philosopher will execute a wait operation on the chopstick when he wants to use it. And then he releases his fork or chopstick by executing the signal operation on the appropriate semaphores. So after the philosopher finished eating, he will have to put back the chopsticks or the forks at their places. So at that time, how will he do? He will be doing so by executing the signal operation on the chopstick or the fork, because we are assuming that they are semaphores. So when a signal operation is executed, what happens? We have already studied that in semaphores, signal operation means we are releasing it. So a philosopher will be releasing his fork or chopstick by executing the signal operation. So how we will be implementing this is, we are having 5 chopsticks or 5 forks. We have seen that in the diagram. So each of these chopsticks will be represented as a semaphore. So what we are doing is we are having an array of chopsticks with the data type semaphore. So the data type is semaphore and we have 5 number of chopsticks. So we are using an array. So what we mean by this chopstick 5 is that we are having an array of 5 elements. So we'll be having chopstick 1, chopstick 2, chopstick 3, chopstick 4 and chopstick 5. So these are the 5 chopsticks we have, and they are all declared as semaphores. And here all the elements of the chopsticks are initialized to 1. So here the semaphore that we are going to use is a binary semaphore, not a counting semaphore, but a binary semaphore. And we know that in binary semaphore, it can take 2 values, either 1 or 0. So don't confuse this with a counting semaphore here. Chopstick 5 actually means it's an array of chopsticks that we are having. Chopstick 1, 2, 3, 4 and 5. And each of these chopsticks can have 2 values, either 0 or 1. So initially all the elements of the chopsticks are initialized to 1. So in a binary semaphore, when it is initialized to 1 means it is free. It can be used by the processes that wants to use it. And if the value is 0, that means it is currently being held by some processes. It is not free. So that is what we mean here. So all the chopsticks will be initialized to 1 initially. Alright, so this is how we are going to make use of the semaphores to solve this problem. So now we'll be seeing the structure of the philosopher. That means we'll be seeing how the code is written in order to accomplish this. So here is the code. This is the structure of any philosopher I. Here what will happen when a philosopher wants to eat his food, that means when he is hungry and when he wants to eat, what is the first thing that he need to do? He need to get hold of the 2 chopsticks that are adjacent to him. So he need to get the chopstick at his left and right. How will he do that? So as I told you, we are going to assume that these chopsticks are semaphores. So he will have to execute a wait operation on 2 forks or chopsticks that are adjacent to him. So for philosopher I, he need to execute a wait operation on chopstick number I and then also on the chopstick I plus 1 modulo 5. So why we are making use of this mode 5 is because, as I told you, the philosopher will need to access the two forks that are adjacent to him. So let's say that we are talking about philosopher 1. So he'll need to access fork number 1 and fork number 2. So chopstick I will mean chopstick or fork number 1, and chopstick I plus 1 will mean chopstick number 2. So this calculation will be going on, but think of the scenario when we reach the fifth philosopher. So the fifth philosopher will need to make use of which chopstick? He will make use of chopstick number 5. So if we just write here I plus 1, then what happens? 5 plus 1 will give us 6, which means chopstick number 6, but there is no chopstick number 6. So after the chopstick number 5, it has to make use of chopstick number 1 again. It is placed in a circular fashion. So it goes like 1, 2, 3, 4, 5, again 1, 2, 3, 4, 5. So philosopher number 5 will need to make use of chopstick 5 and chopstick 1. So that is why we are making use of this mode 5 here. So for example, when we reach the fifth chopstick, what will happen? Here it will be chopstick number 5, I is equal to 5. And here we will have 5 plus 1 equal to 6, and 6 modulo 5 will give us 1. So we will get chopstick 5 and chopstick 1. So that is why this calculation is done here. So this is just a pseudo code. When you will be writing the real code for this, you have to carefully design this one. Okay, so what basically it means is that the philosopher needs to execute wait operation on the two adjacent chopsticks that are placed near him. Okay, once he executes these wait operations, if these chopsticks are available, he will be getting hold of them one by one. And once he has hold of both of them, then he can begin eating. So he will be doing the eating operation here, and after eating, he has to place the chopsticks back where they were so that other philosophers can make use of those chopsticks. So what will he do? He'll have to use the signal operation on the chopsticks. So the same chopsticks that he used here, he will be executing the signal operations for those chopsticks. So signal of chopstick I and signal of chopstick I plus 1 mode 5. So that means he has released the chopsticks and then he will start thinking again. So here we see that when philosopher I is making use of the two adjacent chopsticks, if the philosopher next to him or the philosopher adjacent to him tries to also eat at the same time, he will also try to execute wait on one of these chopsticks. And at that time, he will not be able to get it because it is currently being held by this philosopher I. So we see that two philosophers adjacent to each other will not be able to eat at the same time, and they will not get the same chopstick at the same time. So using semaphore, we have solved that problem. Okay, so now we have found a solution to that problem. But just by doing this, have we solved all the problems? Let's see. So here, although this solution guarantees that no two neighbors are eating simultaneously, it could still create a deadlock. So we have proved that the solution guarantees that no two neighbors are eating simultaneously. We have already explained that. But this could still create a deadlock. And how is that? Suppose that all 5 philosophers become hungry simultaneously and each grab their left chopstick. All the elements of chopstick will now be equal to 0. When each philosopher tries to grab his right chopstick, he will be delayed forever. So think of a scenario when all the philosophers get hungry at the same time. So what will they do? They will simultaneously grab their left chopsticks. So let's say that all of them have grabbed their left chopsticks. Now what will happen? All the elements of chopsticks will be now equal to 0. So whenever a philosopher will grab his chopstick, he will execute a wait operation on that chopstick. So when he executes a wait operation, the chopstick's value, which is a semaphore, will be changed from 1 to 0. Initially they were all 1, they will be changed to 0. Which means that it is now being held by a particular philosopher. So now when each philosopher tries to grab his right chopstick, he will be delayed forever. So let's look at the diagram and understand this. So here the scenario that we are talking about is all the philosophers get hungry at the same time. And what happens? Let's say that all of them will grab their left chopsticks at the same time. So we already explained that they cannot pick up both the forks at the same time. They have to pick up one and then the other. So let's say that all of them picked up the left chopsticks that were at their left. So philosopher 1 will pick up his left chopstick, which is this one. 2 will pick up his left chopstick, which is this one. 3 will pick up this. 4 will pick up this, and 5 will pick up this. Now if you see, all the chopsticks are picked up by one of the philosophers. Now let's say one is trying to eat. So what will he do? He have already got one of the chopstick. Now he needs a second chopstick to start eating. So which is the second chopstick? It is this one. But can he get it? No, because 5 is holding it. Similarly, 2 has got hold of this chopstick which is at his left, Now for starting to eat, he also needs the chopstick that is at his right, which is this one, but it is being held by 1. It is not able to eat it. Similarly, 3 also will not be able to get the right one because it is held by 2. 4 also will not be able to get this because it is held by 3. And 5 also will not be able to get because it is held by 4. So according to this problem, when a philosopher has one of the chopstick, he also needs the other one, and he will keep waiting for getting the other one to start eating. But you see here that each of them are waiting for each other, and nobody is going to release it because all of them wants to eat, and they all have one chopstick each. So each of them, they will be waiting for each other, and they will keep waiting here, and nobody is going to release it. So at this situation, we say that we have reached a deadlock. So this scenario is known as a deadlock. So this kind of same situation can even happen with resources that are shared among processes in our operating system. So this is something that we have to avoid. So that is what we have just said here. So that is a problem that we are going to face here. We have solved one problem, which is no two philosophers adjacent to each other should start eating at the same time. We have solved that using the semaphores here. But still, this problem persists, which could lead to a deadlock. So now we have to find if there are any ways that we can propose in which we can avoid this deadlock. So let's see if there are any remedies that we can follow in order to avoid this deadlock. So here we'll be discussing some of the possible remedies to avoid the deadlock. So the first one is allow at most 4 philosophers to be sitting simultaneously at the table. So here, instead of allowing 5 of them to sit, we will be allowing only 4 of them to sit simultaneously at the table. So the number of forks will remain the same, but the philosophers will only be 4 here. So what will happen? Even if all of them get hungry at the same time and pick up, let's say, the left forks, what will happen? Philosopher 1 will pick up this, 2 will pick up this, 3 will pick up this, and 4 will pick up this one. So we assume there is no 5 now. So we see that one fork is still free over here. So what will happen? Philosopher 1 will pick this up and he will start eating, and then after he finishes, he'll keep it down. And when he keeps it down, 2 will get hold of this and he will also start eating. And after he finishes, he'll keep it down and 3 will get his chance and 4 will also get his chance. So we see that if we avoid one of them, then we can avoid the deadlock situation. So that is one possible remedy that we can have to avoid the deadlock. Then the second remedy is allow a philosopher to pick up his chopsticks only if both chopsticks are available. To do this, he must pick them up in a critical section. So here we saw that in the first scenario, when all of them got hungry at the same time, they just picked up the fork that was available and did not see if the other fork is available or not. So instead of doing that, we will allow the philosophers to pick up their chopsticks only after making sure that both the chopsticks that they need are available. So if one wants to eat, he will make sure that both this and this chopsticks are available, and then only he will pick up one by one. So that is another solution that we can have in order to avoid this deadlock. And then the final solution that we have is use an asymmetric solution. That is, an odd philosopher picks up first his left chopstick and then his right chopstick, whereas an even philosopher picks up his right chopstick and then his left chopstick. So this is an asymmetric solution that is proposed, in which it says that the odd philosophers means here we have numbered the philosophers from 1 to 5. So the odd numbers here, 1, 3 and 5. These are the odd philosophers. And the odd philosophers should pick up first their left chopstick and then their right chopstick. So that order should be followed. And then if it is an even philosopher, he should first pick up his right chopstick and then his left chopstick. So by doing this, what will happen? So we saw that in the first scenario, all of them, when they were hungry at the same time, they all picked up their left chopsticks and all of them ended up waiting for each other. So instead of doing that, we will allow the odd philosophers to pick up their left chopstick first, and then they will be picking up the right if it is available. And for the even philosophers, they will be first picking up the right chopstick and then the left chopstick. So by doing this, we can ensure that deadlocks are prevented. So these are some of the possible remedies to avoid the deadlock in a dining philosopher's problem, even by using the semaphores. So we saw that just by using semaphores, we did not guarantee avoiding deadlocks, but we have to make these small changes in order to avoid the deadlock in this situation. We solved one of the problem using semaphores, but in order to avoid deadlocks, we have to follow these remedies as well. So this is another classic problem of synchronization in operating system. So that is all about the dining philosopher's problem. I hope this was clear to you. Thank you for watching and see you in the next one.